and there's very little research to support those claims, and I think that's something we as science educators should be doing. So many people see that the more practical work you do, the better the type of teacher you are. So if you do a lot of practical work, you're a good teacher, and if you don't do a lot of practical work, you're then effectively not a good teacher. You're not a good science teacher. Good science teachers, certainly in the UK and Europe, do lots of practical work. Now, one of the areas that I'm going to be touching on is the idea of doing with ideas. If I tell you about doing things with objects, many people recognise that's doing things with your hands, and you can imagine practical work is a very hands-on activity. But what I've been working on is the notion that practical work, to be effective, needs to be hands-on, but also it's got to be minds-on as well. And to be minds-on, you've got to be doing with ideas. You've got to be engaging, thinking about things with words. You've got to be thinking about what those words mean, particularly if they're scientific words. And I was in a paper yesterday, and I was really interested that one of the presenters was saying that one of the things they were finding is how important language was in the science classroom, and I think that really is a key point. I think that one of the things that I've noticed is difficult, and maybe, I suppose, those of you who are non-native English speakers, and I had a PhD student who came from Greece, so lots of the words we use in science meant a lot to him, is the fact that some of the words can be strange. I mean, if you think of the word, you're talking to a child in a physics lesson, and you start talking about kinetic entropy, kinetic energy or entropy, these words don't mean anything. They're not everyday words you use. And so not only does the child have to actually think about what the meaning of the word is, they've actually got to learn a new word. And those two things put a lot of pressure on the student to learn. The other thing, and again, I don't know that if this is the case in Korean, but some of the words have non-scientific meanings. So in English, the word force, work, cell and organic have non-scientific meanings. So if you ask a young child in England, what does work mean? They'll tell you it's something that their mother or father does. And so they've got a preconception about work, which you as a science teacher then have to overcome before you can get them to understand what the scientific meaning is. Now, one of the interesting things, and I don't know how many of you, I know from speaking to some of you, you're involved in elementary science education. Research that we have done found that primary school teachers or elementary school teachers tend to be a lot more able to empathise, to associate the problems that young children have in science, because in the UK they don't have much science education themselves. So they understand the difficulties, they understand the problems that children have in learning science. So this was an article that we wrote as a result of a piece of research that we'd undertaken, and we found that primary teachers were certainly able to focus more on helping young children learn than secondary teachers. We weren't very popular for this piece of research because lots of the organisations which are encouraging secondary teachers were saying, are you saying primary teachers are better than secondary teachers? And we said, no, we don't think they're better, but they just understand the problems more. So I'm aware that I've got to speak slowly because some of you probably find it harder to follow. Now, because of that, I hopefully am speaking slower than I would normally do. Okay, what happened then? Primary school teachers allocated more time to their lessons, and so people adapt, and I think that's really important, and what we need to look about is how we adapt in our lessons to changes. So here what we see is the idea of scaffolding, using ideas which can help develop conceptual understanding. And again, there have been some very interesting sessions that I've been to here at the conference about the notion of scientific literacy and why we want scientific literacy. But for me, you can't have scientific literacy if you haven't got conceptual understanding. You've got to have the conceptual understanding in order to engage with scientific literacy. Right, we had again, and I always like going to a conference where when you're giving your paper you think, oh no, someone's already said this, because I think what that shows is people are beginning to think along the same ways. So analogies are something that we've been looking at as part of our research as a way of showing people how they can think about different ideas by getting them to use analogies. Are you all familiar with the term an analogy? Yeah, is that right? Okay. So what we've got here is an analogy works by taking you from something that you know about to something that you don't know about, and it helps you make that leap. So we've got students who come to school, have certain ideas, we want to get them to learn something else, and at the moment teachers in the UK aren't very good about using analogies. So in a way we can use terms, if you like, about, am I blocking your way? Metaphors are statements which allow people to compare and contrast what we want them to know. Now, what it does, it helps. Now, again, I know English is not some of your first language, but I use the term metaphor here because in the literature, the term metaphor is often used, but I think the most appropriate term would be a simile. We're not saying something is something else, we're saying it's like something else. And I think that's an important difference that we need to be aware of. So if we can use analogies and metaphors when doing practical work, can we help students to understand? And that's the thing I'm keen to be looking at. One of the problems, as I said earlier, with people doing practical work is that, and again, there have been other interesting things. I was at a session this morning by an American lady who was talking about work that's being done in America about taking children to an event where they sort of look at how to, I don't know, plan things on Mars. Now, you do get students who then say that was really exciting, they really like doing it. But the question is, what did they learn from it? And I think without the proper use of language and getting them to think about science, it becomes very much an enjoyable experience that has very little learning associated with it. Now, what we are thinking of trying to do, or what we've been doing, is trying to help students move from what I've referred to in articles about the domain of objects, that's about the things that you do, to the domain of scientific ideas, which is what you want them to learn about, and it's about how we can help them to make that bridge, that gap. Now, how do we do it? So the base is a familiar situation, something that you might be familiar with from your preschool environment. The target, the unknown situation that we want them to learn about, and what we're going to use an analogy, some kind of metaphor to help them cross that boundary between the two. And that's where we're going. They can provide a step then, which helps in observations of practical lessons, and helps the student to actually understand the conceptual basis for why you're doing the work that you're doing. Now, what we're trying to do, if you like, part of the problem that I think that students have with ideas, and maybe this is, we were talking about this over lunch, why is it when we talk about STEM, we talk about STEM as a general, if you like, a single subject, but the S in STEM is for physics, chemistry and biology, and the differences between those subjects are often overlooked. So we don't have a problem of girls in STEM. Girls like doing biology. More girls do biology in the UK than boys. The same number of boys and girls do chemistry. It's only in physics that we have less girls than boys. And what we want to do is we want to help them think about the ideas, and maybe by using analogies which interest girls more than boys, we can get more girls interested in doing physics than otherwise would have done. Now, if we've got here's an example that if you're trying to help people to understand, you're doing an investigation some practical work which is looking at the effect of concentration, temperature, surface area on the rate of a chemical reaction. How can we help them make the link for students, observations and the scientific ideas? What can we do to help them? One of the pieces of work that I was involved in a few years ago now was the use of drama to help people engage themselves, because if people can actually feel or do something, they can use that as an analogy for understanding. So what you can have here, the metaphor, students can be dancing in a room to represent the moving particles. When they meet with other people in the room, these can represent the analogies of collisions. And in this manner, students can be helped to think and talk about their observations by seeing what they themselves are doing. So this is a way that we've looked at how we can use a metaphor or simile for the speed of running compared to temperature. So this is one of the ways we're trying to help people engage with the idea rather than just remain superficially looking at something and not thinking about it. Okay, now what we're really doing here, we're providing, and you're probably familiar with the word Vygotsky's idea of a scaffold. So we're looking to scaffold ideas and to help them, and this is work that I did with a colleague of mine back in 2014. I'm going to skip these because I think I've explained enough to you to understand what the role of the metaphor is. It's important to point out that poor analogies can be very problematic. As an example, if you use an example of burning wood or paper, and yet you wanted to use this analogy to help students, have you seen where you take a piece of wire wool and you can burn the wire wool? Wire wool, you familiar? What happens is if you ask the students to make predictions, they'll tell you that if you burn wire wool, it'll disappear like burning a piece of paper. But the problem with that is obviously when you burn the iron wool, it oxidizes and its mass increases. So that use of analogy generates a misconception. So we have to think very carefully about what analogies we're going to use. Another thing that Glyn has pointed out is we have to be careful simply about the using of a same word. It can be that important. So if you talk about closing an electrical switch, we tend to mean the electricity will work, the sound will work, whereas if you close a water tap, you actually turn it off. So when you speak to students and you told them you're closing the electric circuit, they imagine you're actually stopping the electricity because they draw on this analogy that they're used to in everyday life. So it offers important opportunities, but we've said there are some problems. Now, you've got to think in the way, as Gunstone says, about those observations in the way that the teacher would want you to think. Now, one of the interesting things is that students can sometimes learn things that you might not have wanted, and then you've got to think, well, can we use that? Ideas are difficult. There's no doubting. I think one of the reasons that students say they don't like physics is because physics is difficult, because physics has maths in, and maths is difficult. And if you look at biology, it has less maths in, so it's less difficult. And I think that kind of problem solving is something that people find difficult. Okay, we've looked at this, Pardo and Parker, the idea of incorporating analogies and metaphors to help students see the phenomena in the same scientific way. So you have all got, I imagine many of you have got a scientific background, so if I give you a problem or you think about a problem, you think about it in a particular way. And in a Kuhnian sense, you've joined the scientific paradigm. You think about things in a certain way. Now, breaking the boundaries. This is what this conference is all about. For me, it's to make practical work more effective, as I said, in developing conceptual understanding. Now, include objectives. I think we have to include objectives that relate specifically to learning about ideas. But educators also need to think explicitly how they intend their students to learn about those ideas. So the idea that if you do a piece of practical work, your students will somehow absorb all the knowledge you want like they're just sucking it up like a sponge is wrong. I think teachers and science educators have to think a bit more carefully about how they're going to do that. And we think that teachers should be thinking about what analogies, what metaphors can they use to help them do that. So a little bit there about work we've done about the cognitive challenge of linking observations effectively, what we can do, and the difference between primary or elementary and secondary school teachers. What I want to come to now, I think, is the important part. I'm very much of the view that too much educational research is what I call opinion-based. You'll go somewhere and someone will say, this is the way we should be doing it, and you ask them why, and they say, well, it makes sense, I think it's a good idea. I think educational research has to move away from just being good ideas, and it has to be evidence-based. The role of educational researchers, from my point of view, is to carry out studies which look, collect data, analyse the data, and say, this is what works, this doesn't work, rather than simply saying, I think practical work is a really good idea because I like doing it when I was at school. That to me that's just opinion. So back in 1999, Miller, I should point out, I like Robin Miller very much. He was my supervisor. He developed a model for looking at effectiveness of a task. And what he does, he simply says, let's think what the teacher wanted to do before the lesson. What was the teacher going to get the pupils to actually do? Then we look at what the pupils actually did in the lesson. This is why educational researchers should go in and look and see what the students were actually doing. And also, what did the students actually learn?